1:30 work session over in Enid. So I will be over in Enid, and I'll do my 1:30 work session there. I will give you guys in Enid a heads up. Next Friday, October the 11th, there is a massive meeting for all faculty at 1:30. So I will not be able to hold the session at 1:30 because there's a massive faculty meeting at 1:30. So just be aware that next Friday, I won't be able to be there. So if you're having study concerns, because the next test is October the 16th, and that's going to cover chapters 4 and 5, because we're starting chapter 5 today. It's on October the 16th, which is the Wednesday before fall break. So that kind of gives you a heads up. So those of you who are studying and starting to study and get ready for the test, again, I'll be available to help work questions and problems. And for those of you who I've been working problems with over email, it really is helpful if you take a picture of your work and send it in with your question so that I can look at it, because sometimes it is a simple mistake. And it's not even a mistake, really. It's you plugged in the wrong number. And looking at what you have and looking at your number, I can say, look at your number again. So that's easy to do. If you take a picture of your work and send it in with your question, that does help me a lot. And I can do a Zoom with folks. It's not the best, but I can do a Zoom so that I can work with you and you can ask me questions directly. But again, it's helpful if I know which questions that you're having issues with. I did get a request, and so you will notice that there is a new assignment that popped up on WebAssign. It is for your purposes only. I am not grading it. It is not available for extra credit. It is there for your purposes only. And I have gone in and I have added questions that are kinematics questions, both just the general linear kinematics, two-dimensional kinematics. I put in questions associated with forces, vectors, and I've put in energy questions as well. So there are some questions that are available for you to look at. Yeah?
Is it the one that says due October 11th?
Yeah. Oh, well, does it say due October 11th? I thought it said it due 16th. The homework for chapter 5 is due the 11th.
Okay.
Yeah, that's what I was thinking.
Homework for chapter 5 is due the 11th, but it'll say like extra problems, or it says extra problems or problems for studying or exam prep or something like that, and I have it due the day of the exam.
Okay.
And the only reason I have it due the day of the exam is that way you got to kind of gauge it for the exam. You get 50 tries per problem on that one, so it's kind of unlimited. But if it's taking you 50 tries, at that point, folks, if you've, you guys know now that if you've entered it in like 3 times, because I think WebAssign's giving you 5 tries, right? And if you'd entered it in 3 times, that's usually when some of you are going, okay, I better ask the question. That's usually a good sign, asking the question. 2 times is usually if it's a format problem, right? 2 times is, did I put the e to the minus whatever incorrectly and I've just screwed up on my format. 3rd time, it's like, I've obviously got something that's not quite right here. I better ask the question, so that you got 2 more opportunities. You got 1 opportunity to get the hint, right? The hint. And then you got 1 opportunity to really figure it out. But if you're taking more than 5 tries on the 4 whatever, that out there, that's usually a good point to ask the question that there's something wrong. So it's there for you. You can go in and look at them. You can do which problems that you want to do, or that's up to you. I do have the link in there if you're not liking our book. Okay, I like our book because it has some really good examples in it. But there are times that the explanation doesn't necessarily jive with the way you think. The OpenStax college physics book is very, very good, and it's free. It's a PDF. It's free. You can go out there and look at it, and it has different examples in it. So there, you can use that for examples. So that's another resource for you. And then I try to post extra resources as well. So other questions? Because that did remind me about those two things. Okay. You guys good over in Enid? All righty. I'm going to hit, I got the record going, so we're going. Okay. So, oops, forget to punch one more thing. There's so many buttons to push. Okay, can you see? Yep, you guys can see the document camera over there. Document camera's not up on this one yet. Ah, there we go. So far what we've done is we've had that general trig stuff where we've dealt with our triangle, right? And we've used that triangle over and over and over again. We've dealt with vectors. And we've done our kinematics equations. And then we've got our laws of motion. Where we got F is equal to ma, forces come in pairs, an object in motion remains in motion unless acted upon another force. We have Newton's law of universal gravitation. Okay? So we've done a number of things. And so far, everything that we've dealt with has had direction and magnitude to it. Definition of a vector is it has direction and magnitude. And when we've done our forces, we know that the force is in the same direction as my acceleration. And we've also done the first condition of equilibrium, which was the sum of the forces equals 0, and that was for equilibrium. Sum of the forces equals 0 for equilibrium. So we've got a variety of different things. But now, everybody's had general chemistry, right? I've got nods. Everybody's had general chemistry. Everybody over Nina, y'all have had general chemistry, right? Okay. And we all talk about Hess's law. Everybody remember Hess's law? Over on the thermodynamics side, the big key thing about Hess's law was that we didn't care how you got there. We only cared about where you started and where you finished, right? Don't care about where you got there. We always start and finish. So Hess's law says we start and finish. So let's take a ball, and we're starting at ground level. Okay, we got a ball, we're starting at ground level, and we move that ball up. Now, if I'm in general chemistry, we've done a couple of things. We've talked about this. One of the things, everybody remember the hydrogen lines? We did the spectroscopic lines in hydrogen, and we take a hydrogen tube, and we get those little electrons excited, and those little electrons jump up from one energy level to the next, and then when they get, they relax, they jump back down and they give off a photon in a specific color, right? So we're jumping from one end, and of course in chemistry when we talk about that, that is when it is, we call those quantized because they're specific solutions and they're in quantum energy levels. But if I have a ball that I'm lifting from the ground up, I don't necessarily have those quantum levels, but I am doing something. I'm exciting the ball essentially, just like I excite that electron, and I'm moving it from ground level to some other level up. And then we know what happens, right? If I let that ball go, it's going to fall to the ground. And we've played with that over and over and over again. We've talked about what's doing it. Gravity's a field force, and it's going to have that ball fall down. But we haven't really talked about, well, there's that thing that we know, because we've seen it in chemistry, that we now have an energy of position, okay? We now have an energy of position. And that energy of position, we can look at a couple of different ways. One is, okay, we're going to start out. I don't know if did anybody ever give you the definition in chemistry? I've had some of you in my chemistry class, so I know you heard it in my chemistry class. But has anybody ever given you the definition of energy?
I haven't heard yours.
You haven't had mine? Okay. It's my favoritist definition of all physics. And I am being facetious, because until you understand it, the definition means absolutely nothing. So, what we're doing is we're starting with energy, and we're looking at energy, and energy is the capacity to do work. And until you understand this definition means diddly squat. But it is very, very accurate. So let's think of why we give this definition the way we do. So let's look at, so for my ball, lifting my ball from the ground level to some point higher, I've had to do work, okay? In order to get the ball from the ground to some point above, I've had to do work. And we'll define that here a little bit better in just a second. But I've had to do work. But if I want to look at this definition and really understand it, let's think about the Industrial Revolution. I know that seems odd, but physics ends up being a history lesson more than it ends up being anything else. One of the things that we did work with and got things going is I would have my water wheel, and I'd have water come in, and it would hit the little paddle, and my wheel would turn, right? And the water is just falling down, and it goes on to the stream below. Now, if I think about a water molecule as a little ball bearing, I have a stream of ball bearings that are hitting this paddle, that's causing this paddle to turn, that's causing this water wheel to move, and they're all coming down here. So all of these things, the water has energy at the top that we're actually using to turn the wheel. And the whole idea of turning the wheel was that I could turn a shaft, and I could use that shaft to turn a grindstone for a mill. I could use that shaft to drive a belt. I could use that shaft to do work. Which is where our concept of work comes from. And this is mechanical work. Okay? This is mechanical work. But basically what I've got is I've got the water, using the water, and I'm using its energy of position and its changing of that position in order to accomplish something. So one of the things that we get with this is we're going to define work. And I'm going to write it out in its normal mathematical form. And I'm going to put a dot there. And that dot refers to a dot product. And even though you guys were doing it algebra based here, just as something to be aware of, that this dot product is a mathematical thing that's going to allow me to get rid of the vector character. Okay? It's going to allow me to get rid of the vector character, and work is going to be a scalar-only quantity. So all of a sudden, we're not going to have to worry about direction. We have to know where we start and where we finish, but we're no longer going to necessarily have to worry about direction too much. At least when we get the value for work. So let's look at it a little bit differently. So if I take my ball and I lift it up, I'm going to do work on it. And that work is going to be related to the force. I'm going to leave my little dot in there. And my distance. So if I'm lifting the ball up a height h, that's my distance. The force that I have to use to lift my ball up is the force we've been playing with for a while. It's good old weight. I have to overcome the weight of the object, and I have to move it up, h, and this becomes mgh. So the work that I do goes into potential energy. So in this case, I've got, and this is going to be a negative because it's opposite. Work and potential energy are opposite when I'm dealing with direction. But I've got a change in potential energy. Now your book is going to use things like U for energy. I like to go ahead and use PE so that it's clear that we're talking about potential energy. So in my notes, we're going to use PE to refer to potential energy. And so my work is going to equal my change in potential energy. Turns out my work is going to equal my change in energy of the system, and we'll talk about that as we go through. But for right now, we're just looking at this particular system, and it's the potential energy. So if I deal with Hess's law, remember Hess's law, we usually show you the picture of the mountain. And the idea is I go from this state to this state, and I can either do it by going straight up, or I can do it by going the twisty-turny curve. And the idea is I've started here at this level, and I end up at this level, and it doesn't matter how I got there. Same with work, because we're looking at my change in height. So I get this potential energy that's a change in height. So this one, it comes pretty clear that I can do just a straight multiplication. But now let's take, because we've done this before, I've got a wagon, and it's loaded up with stuff. And I'm going to move this wagon from here to there. And let's say that that's 10 meters. And this is where the dot product comes into play. If I want to move this wagon, we know the biggest bang for our buck, to get the most efficiency out, I need to apply the force directly in line with the motion that I want to achieve. Right? If I want to get the most efficiency out of the system, that's what I've got to do. But that's a little red wagon, right? It's just like my suitcase, right? And so normally what happens is I have a handle and I'm applying a force like that. And that means we end up with a little bit of an angle. So I end up with that angle, and I'm going, okay, so if by doing this, we do this out of convenience so that I don't have to get on the ground and be in the exact same line as this, but in order to do that, I'm going to give up some efficiency. I'm going to give up some efficiency. And so this becomes, I'm going to end up with a force cosine of my angle in order that this will be the part that actually goes into the work that's being done. And that's our normal definition. So work ends up being force cosine of the angle times distance, or I can have my force times distance cosine of the angle. And this gives me my scalar product, which means now I don't have to worry about direction anymore. I am just worrying about the fact that whatever my force is in the same line as my direction is what's going to ultimately go into my work. So if I apply here a 50 Newton force, and I'll give you a caution here in just a second, the 50 Newton force, and let's say that this angle is 30 degrees, the work that I do in order to go this 10 meters is going to be my 50 newtons, my 10 meters, and my cosine of 30 degrees. So this is going to be 500 times 0.866, and this is going to be weird units of Newton meters for right now. It's going to be 433 Newton meters, and we're going to define a Newton meter as a joule, and this will be 433 joules.
How did you get that?
It's cosine of 30.
Oh, so I do all that separately? Okay,
My recommendation, because all of you have calculator issues,
yes.
okay? Let's see if I can scroll into the calculator. It'll give it to me. Okay, we got it. If I were to do cosine of 30 degrees times 50 times 100, I get some weird thing like -5. Okay? Depending on how you entered in your calculator, it'll be weird. So if I do 50 times 10 times the cosine of 30, and do it all at once, I get 433. I worry about my order of operations. Now the other calculator, like the one you got, the one that's the white one, that one has a tendency to do really weird stuff to you, you know, and it does really weird things because of order of operations. So a lot of times, I will do it in separate pieces to keep myself straight, so that I'm not worrying about order of operations in my calculator. The other reason I did this is because I want to show you that the cosine of 0, and that would be if my force is right in line, cosine of 0, so I've got my number, my cosine of 0, if I do this, cosine of 0 is equal to 1. So I get my maximum work if I'm in line with the direction that I'm going. I get no work if I'm at 90 degrees. Cosine of 90 is equal to 0.
I'm not getting the right answer. This is weird.
Now, make sure your calculator is in degrees, not in radians or gradians. That's one thing. Okay, all right. So work is the force over a distance. We're doing the force over a distance, and that gives us work. Let's look at a situation here. Oh, I want to do something else real quick. So let's look at this. Couple of other things. So we're going to take a weight, okay? We're gonna take a weight, and my problem is gonna give me that this weight is 15 newtons. And we're gonna lift it 1.5 meters. And we wanna calculate the work. So work is going to be force times distance. I don't have to worry about the angle because my work is being done in the same direction. My work's being done in the exact same direction. And the way my problem gave it to me is it gave me a 15 Newton weight. And I have to move it 1.5 meters. I'm just going to put in my 15 times my 1.5. Going to equal to 2.5 joules, because this is in newtons and that's meters. Now, if you see this on Chegg or whatever, on a Watch It or whatever, and you're working the problem and you go, okay, I'm working my problem, I got my 15, I got my 9.8, I got my 1.5, and I get this number. And you plug this into WebAssign, and WebAssign says that's wrong. And you're going, what did I do wrong?
You're not supposed to multiply by 9.8 because it's Newton.
Right. It's already given it to me in newtons. I don't need my gravity. Don't need gravity because this is in newtons, this is in meters. If I put this in and I actually write in my units, you can see it right off the bat that you've got a problem. Now, if I told you that this was a 15 kilogram weight, then that would be the answer. Because I have to include, to get my force, I have to get my weight. My weight is a force, and I do get that as my answer. So one of the things you've got to watch is what units they give you, because that's one of the critical things that we have. Now, this is a Newton meter. We are going to see Newton meters again that aren't joules. This is an energy, so it's a joule. Because there are two ways to take vectors and mathematically handle vectors. So this is mathematic vectors, okay? Mathematics, okay? I can have, and that's why I was very careful to put a dot. Okay, very careful to put a dot, because I could also do something like this. And in fact, we don't do it that way. We do it this way. And this is a cross product. And this result gives me a vector. Okay? This is a cross product and it gives me a vector. This is a dot product and it gives me a scalar. This will give me work. And we'll see this one later, and this will give me torque. So we see this one later, but right now we're focusing on this one. But because we're talking units, you'll see Newton meters down the way that aren't joules. Right now our Newton meter is defined as a joule. But we're focusing right now on the work side, not the torque side. Because this gives me a vector. So let's get our first tool. And this is a legit tool. So I'm going to start out with my 15 Newton weight. And I want to raise it 1 meter. Okay? I can use a lever and move through a distance of 1.5 meters, and I want to know the force required. This is why levers are cool things. The work that I'm going to do here has got to equal the work that I do over here. Because it doesn't matter where I start and where I finish, the object's the same. This 15 Newton weight is going to move up 1 meter. So if I do that, that's a 15 Newton weight. I'm doing it a height of 1 meter. This is going to give me 15 joules. So over here, I have to apply 15 joules, which is going to be my force times the distance that I move it through, which is 1.5. So I'm going to take my 15 joules divided by my 1.5. It's going to give me my force that I have to apply. And that should be like 10. But it's early in the morning. So I end up with 10 newtons, because that's Newton meters divided by meters is going to give me newtons. I only have to apply 10 newtons of force to lift that 15 Newton weight. If I were over here, I'd have to use 15 newtons to lift that weight. I'd have to, so by using a lever, I reduce the amount of force that I have to apply, which is why we like levers. Levers are cool, because I don't have to apply near the amount of force in order to lift that weight. Okay? We can use the same principle. I got a loading dock. Okay? And this is why getting rid of vectors is nice. I'm going to raise my 15 Newton weight by 1 meter. So I got my weight, it's 15 newtons. I'm going to go up this loading dock here. And this we're going to say is, we're going to do it as 3 meters. So the length of my ramp is 3 meters. The height that I'm ultimately going to be is 1 meter. The work that has to be done over here, we already figured that out, that's 15 joules of work. I can apply a force here to go up. My force times my distance, because I'm pushing it in the same direction as the ramp, is going to equal 15 joules. My force is going to only be 5 joules, or 5 newtons, sorry, 5 newtons. Because I moved it over 3 meters, and so my ramps are my other tool that's really cool. Because the same amount of work here is the same amount of work there. It doesn't care how I got there. So work is handy. Okay, so we're going to go back to our ball example. We're going to go back to our ball example. So I've got a ball. And we're going to raise it for a distance, right? We're going to raise it up a height h. So I've now done work. And we've already said that this work is going to equal a change in potential energy, and I'm going to use magnitude. Okay, at work's change in potential energy. Except now I'm going to let the ball fall. Okay, I'm going to let the ball fall. And if I do this, remember we started with v squared is equal to v naught squared plus 2ah, because we're doing it through a height h. I'm going to solve for h over here. Okay, I'm going to solve for h over here. So I'm going to get v squared minus v naught squared divided by 2a is equal to h. Everybody with me? So work is equal to force times h. But my force in this case is going to be mass times acceleration. We just have to know what that is. But now I'm going to plug in for h, and I got v squared minus v naught squared divided by 2a. My a's cancel out, and now I have mv2 divided by 2 minus mv naught squared divided by 2. We're going to define 1/2 mv squared as kinetic energy. Okay, your book doesn't use the U and the V's. A lot of books do. I was just double checking. Okay, I was just double checking on how your book is using it. Because a lot of times you'll see the letter U and you'll see the letter K as defining which one's kinetic and potential energy. Our book actually leaves it as PE for potential energy, KE for kinetic energy. Okay, this gives us our so I got my kinetic energy is defined as, there's my work. Like I said, when you're working your homework, best thing to have with you, if you print out nothing else out of your book, having your summaries printed out helps you bunch, because it has all the equations that you're going to be working with. It has all of the fundamental concepts that you're working with. And I was just double checking to make sure that we have the right, so that you guys, but if you pick up another book, just look for what the units they're going to use, what symbol that they'll use for kinetic energy and potential energy. And usually the letter U will show up. So back here, we had work was related to a change in potential energy. Over here, we get work is related to, because this just becomes a change in kinetic energy. So we end up with what we call the work energy theorems. And depending upon your situation and your problem, the work is going to equal the change in kinetic energy, or the work is going to equal the change in potential energy. So let's kind of think about this one for a second. All right. I've got a target here. And I have a little bullet that's going to enter the target with a velocity of, we'll give it 50 meters per second. And I'm pulling numbers out of my hat, so that means that this may not be a physical property here, that this may not actually physically be a realistic problem, but we're going to try it anyway. And we're going to give this bullet a mass of 0.1 kilograms. So I've got a bullet that's going to hit the target. It's got a mass of 0.5 kilograms. And it's going to end up somewhere in the target here. With a velocity of equal to 0. We want to know the work done by the block on the bullet. Now, listen to what I said. We want to know the work done by the block on the bullet. Because when we talk about work and energy, we have to look at systems. And when we talk about those systems and we start dealing with what you guys got in thermodynamics, we have to be very, very conscious about where things are being done. Is it, if I have an exothermic reaction, I have heat leaving the system to the surroundings. If I have an endothermic reaction, I have heat coming from the surroundings to the system. And work and energy are related. Work, energy, and heat are all related. So if I want to do this, I want to find the work. The work is going to equal the change in kinetic energy, and in this case, my 1/2, the mass, is going to be my velocity final squared minus my velocity initial squared. And when I plug those numbers in, I'm going to have 1/2 0.1, and my final velocity was 0. My initial velocity was 50 meters per second squared. So if I plug those numbers in, gives me 125, a negative 125 joules. So that's the work done. That's the magnitude of the work done. And the question is that negative the block working on the bullet or the bullet working on the block? And in this case, we figured out the bullet. So this is the work done by the bullet, or the work done on the bullet. So I would have to worry about that negative and plug it in. So you may end up getting the answer correct, and the positive and negative, depending on how WebAssign has asked the question, you may have to make sure you've got your positives and negatives correct. But my work is going to be related to the change in kinetic energy.
So it would be negative
Because the bullet's going from a velocity to a stop. And the places that we see that a lot, just so you guys are knowing what we see, is, and this comes back, going back into chemistry, because we've seen it in chemistry. If I have a piston and I'm pushing the piston down, right? If I have an ideal gas, I'm pushing the piston down. I'm doing work on the gas, right? And if I do work on the gas, what happens to the gas when I compress it? PV equal nRT, right? So if I'm increasing the pressure, decreasing the volume, what happens to temperature? It increases. So if I'm, and this is one of those things, if I'm doing work on the gas, the temperature's going to increase. I'm increasing the internal energy of my gas. Right? And if I have the gas explode in here, like in my car, and it pushes up on the piston, work is done by the gas on the piston, and I have to just keep track of where my energy's going. And that's one of those things that we end up with, and it becomes critical in chemistry and in engineering. We're following where the heat goes. And when we follow where the heat goes, that tells me where my work is. So you end up with these, and depending on which discipline you're in, depends on whether you're doing positives and negatives. Because if I am in engineering, I want to know what's happening to the piston. If I'm in chemistry, I want to know what's happening to the gas. So I'm going to set up my sign convention to tell me what I want to know. Right? And so you have to be very careful when you're exchanging different books, because if I go to a physiology book and I'm worried about the work that the heart's doing on the blood, I might have a different way of looking at the positive and negative. Okay, I just might have a different way of looking at the positive and negative, because work, energy, and we usually use a Q, right, for heat. Physics 2 will use a Q for something else. But this is work, energy, and heat. They're all related. And one of the fundamental principles of chemistry is conservation of energy. Energy is neither created nor destroyed, it just changes form. So if I go back over here and I'm looking at that just changing form, we start out with a ball at ground level, we do work on the ball, we get it up there, we now have potential energy. Okay, now I have potential energy, and the work was equal to the change in potential energy. Well, if I let the ball go, the ball's going to fall, I go from potential energy to kinetic energy. But all along, the work that I put into the system and the kinetic energy that I get out should all be equal. And then if the ball is somewhere in between, I've got potential energy plus kinetic energy, because I have conservation of energy. Now in this system right here with my ball, the work that I've done to put in potential energy, and I drop the ball and I let it fall down and I get my kinetic energy out, I shouldn't be losing anything, and these are called conservative work. And we usually put a little C on there for conservative work, because now if I have my piston, we know we got another problem. I'm going to produce heat. Heat is non-conservative work. Heat is non-conservative work. I can't, second law of thermodynamics is going to tell me that I can't keep all the heat in the system. I can't break even. I still have conservation of energy, but I can't put all of that energy into work when I have and generate heat. So my total work, or my total energy is going to be the sum of my conservative energy plus the sum of my non-conservative energy, and that non-conservative energy 9 times out of 10 is heat. Because we know that I can do work on my hands and use friction, and that friction is going to give me heat, and I can't use all that heat, and I'm losing some of my work, I'm losing some of my efficiency. I'm losing some of that efficiency. Your internal combustion engines are only about 40% efficient. So all that energy that the gasoline that we use for gasoline, all that internal energy stored in the gasoline as part of chemical energy And when we use it for the explosion in the piston to drive the piston, we're only getting about a 40% efficiency. Works pretty darn well for what we want to do, but we're only getting about 40% efficiency. So we get energy is conserved. So we end up with total energy is going to equal potential energy plus kinetic energy plus other energies, which usually is heat. And those are non-conservative ones. Could be light, could be sound, because if we explode something, right, we hear it, we see it. So we do have other energies, but most of the time it's going to be heat. Most of the time it's going to be heat. Couple other things that we want to look at, just so you have it so you can start working problems. We can do a potential energy of a spring. And one of the things that we know about springs are, if I can compress the spring, and I have something that's holding it there, and I release it, the spring is going to push out, right? We know the spring is going to push out. And then if I stretch the spring, we know the spring is going to want to go back. And it turns out that my potential energy due to springs is going to be equal to 1/2 kx squared. So this relates back to Hooke's law. 1/2 kx squared. And if I look at it, and so this gives us another way to look at work. Okay, this gives us another way to look at work. If I plot a force versus stretch on a spring, force versus stretch on a spring, if I plot that, because we know how Hooke's law goes, I get a straight line. And now if I want to figure out the work done to stretch my spring, it's going to be the area under this curve. It's going to be the area under the curve. And if I look at that, we go, okay. If I have this and I look at my area and I'm looking at this, this is going to be 1/2 kx squared. Because my force over here is kx, my Hooke's law. If I did this as a rectangle, it's going to be kx squared. My triangle is only half of that. So the area under this curve is equal to the work. It's another way of figuring out work. Total another way to figure out work. And then we use springs. Springs are great things to store energy. Okay, so I'm going to do my famous diagram. So I've got a slide, right? I got a slide. we're gonna take a 25 kilogram kiddo. We're gonna take the 25 kilogram kiddo up to the top of the slide. The slide is 1.5 meters high. We want to calculate the work to go to the top of the slide. We want to know how fast the kiddo is at the bottom of the slide. Okay? We want to know the work that's done to go to the top of the slide, and we want to know how fast the kiddo is at the bottom. And we want to know how fast the kiddo is at this point right here, which is at 0.75 meters. All right, the work is just going to be my 25 kilograms times 9.8 times the distance, 1.5. This is meters second squared. This is going to give me kilograms, meters squared, seconds squared, which is going to give me joules. So I'm going to take my 25 times my 9.8 times my 1.5. Gives me 367.5 joules. The work that's done is equal to the potential energy at the top, which is now 367.5 joules. Conservation of energy says the kinetic energy at the bottom is going to equal the potential energy at the top. So my kinetic energy at the bottom is 367.5 joules. My total energy right here is going to equal the potential energy plus the kinetic energy, which is going to equal 367.5 joules. Provided I'm not losing anything to friction. And over the course of the slide, one time down, probably not losing very much. So I've calculated the work. I now know the potential energy. I've calculated the total energy because I know that at the top. I've got it at the bottom, so I'm going to get my 367.5 joules are going to equal 1/2 mv squared. So that's going to be 2 times my 367.5 divided by my 25 kilograms is going to give me v squared. It's going to give me 29.4. And this is in meters squared, seconds squared. Gives me 5.4 meters per second at the bottom. Now if I want to find it at 0.75 meters, I've got 367.5 is equal to the potential energy, which is the mgh plus 1/2 mv squared. So I'm going to get my 367.5 minus 25 times 9.8 times 0.75 is equal to 1/2 mv squared.
So how did you get the 5.4? Did you divide it by?
Square root,
Huh?
take the square root.
Oh.
This works out to be 180, oh no, that's the whole thing. 183.75 is equal to 1/2 mv squared. V squared ends up being 14.7, and that's meters squared, seconds squared. V ends up being 3.83 meters per second. You guys all with me? Okay, because it's the same thing as you get before. Somebody's always going to ask me, well, what equation do I use? Unfortunately, you got to create your own equations. You get to create your own equations depending upon the situation. I'm going to stop there.